let's see if I can get screen sharing to work. Okay, so I'm a third-year PhD student at Berkeley. I'm currently advised by Rin Ung. Before Berkeley, I was at MIT, where I did a master's with Ramesh Raskar and Fredo Durand. And yeah, so today I'm gonna actually talk about two papers. So both of these are on behalf of the many collaborators I've worked with, and both of them involve exploring coordinate-based MLPs. And the first one's really about how you get these networks to represent higher frequency functions. And then the second one is about how you initialize the networks. And so I'll just sort of hop right in and start with this first one called Fourier features let networks learn high frequency functions in low dimensional domains. So as many of you probably have noticed, there's been a lot of recent progress in computer vision and graphics that use these simple fully connected networks, also known as multilayer perceptrons or MLPs, to represent 3D objects or scenes. And the core idea is that they take in a single coordinate and then they produce the value at that coordinate. So for example, you can have an MLP that takes in a 3D coordinate and then outputs a binary value indicating whether the point lies inside or outside the 3D object. Now, this is fundamentally a continuous representation, and it can be densely sampled to recover the encoded shape. So in contrast to the uses of typical deep neural networks to represent high frequency functions or high dimensional functions, here we're trying to get an MLP to represent a complicated function on a low dimensional input. So as a simpler example, we can use an MLP to represent an image by just taking in the 2D pixel coordinate, x, y, as input, and then outputting the RGB color at that coordinate. And this is what happens if you do that. So over the course of training an MLP to represent this image, what we see is that the network struggles to learn the high frequency details, such as the fur in this fox image. And we find a simple technique that is able to solve this problem. Instead of just inputting the x, y low dimensional coordinates into the network, we first pass those coordinates through a Fourier feature mapping, which just looks like a set of randomly scaled sines and cosines. This allows us to control the frequencies that these MLPs are able to represent in practice. So with this technique, the MLP quickly learns the high frequency details in the image. So as you can see on the right image, this is what happens when you add the extra information. On the left, it's sort of your naive version. And we can understand why the Fourier feature mapping helps us by looking at some recently proposed connections between deep networks and kernel regression methods. And before I explain this, I'll just briefly describe how kernel regression works. So kernel regression is a method for non-parametric function estimation that takes in a set of input-output XY data points and then estimates a continuous function fitted to those points. These estimated functions are always, the estimated function is always a linear combination of these base kernel function elements, one centered around each input data X value. And these typically resemble like a Gaussian bell curve or some other blob-shaped curve. Adding them all up produces a continuous, the continuous estimated function. And then these W values are set that the function passes as closely as possible to all the input points in like a least squares sense. And now, as you can guess, it's really critical to pick the correct kernel functions. And if the kernel is too wide, what you'll see is that you won't be able to represent high frequency details. And if the kernel is too skinny, you end up overfitting to the input data. So to help visualize this, here's a sort of a simple visualization where we show the effect of fitting a 1D function, which are these yellow points shown on the right image, with a kernel regression. And the blue line shows the kernel regression estimate given the input data using the kernel that's showed on the left side of the image. And I've also added this red marker here. I can't put my mouse on the screen. Oh, there we go. Yeah, so I've added this red marker here that is the same width as the distance between these two yellow points to kind of give you context on the size of the kernel. So right now you can see that the kernel is much wider than the distance between points, and as a result, you get a regression that is, or a function estimate that is too smooth. On the flip side, if it's too small, we see that the function overfits to the data points. So it's clear that the shape of this kernel function is very important for accurately reproducing your target signal. So now going back to this connection with neural networks, there's been this recent explosion of ML theory work that has produced pretty incredible results that precisely characterize the behavior of a network during training under certain conditions. And the basic takeaway is that when you train with a sufficiently wide network, it performs kernel regression with a certain known kernel. And the cool thing is when we use these Fourier features to modify the input, this changes the width of the kernel, and it makes it much better suited for the tasks that we're interested in. Now, the exact form of the Fourier feature mapping is this. We sample a random matrix B that is very tall and is basically a long list of random projections of the input coordinate. We then pass these projections through a sine and cosine function. And it's worth noting that all you have to do is sample this B matrix once, and then it's fixed during training. So this is just a deterministic mapping and is not another network layer. Now, this general mapping is the exact same as the random Fourier features that were proposed in Rahimi and Recht in their seminal work, the features for large-scale kernel machines. So just to give some intuition, I want to show a basic example in 2D where we sample each row of the random B matrix from a Gaussian distribution. So here we're plotting the input coordinates on a regular grid sampling of 2D points. So increasing x1 from 0 to 1 results in a ramp from left to right, and then similarly increasing x2 is results in a ramp from the top to the bottom. After passing them through the Fourier feature mapping, we get these sine waves at different frequencies that are tilted due to the linear combination of x1 and x2. Remember that the way we'll process these is by stacking them all up in the channel dimension and then processing each individual pixel with a fully connected network. And what you notice between looking at these, it's not that hard to imagine why passing the thing in on the right compared to passing the thing in the left is able to capture these much higher spatial frequencies. But we can actually justify this theoretically too. So we're going to use the neural tangent kernel theory, which for a standard fully connected network, the corresponding kernel can be expressed as a scalar function of the inner product between two input points, so x and y. Now it turns out that our Fourier feature mapping has a nice property where the dot product of two feature vectors is actually a stationary function of the two original points x and y. So this means that it is shift invariant. If we move x and y by the same amount, their feature dot product stays the same since it only depends on the difference. As you can see here, the subtraction. Whereas without the mapping, if you were to move the two original points the same amount, your feature dot product would change, which is not a desirable property. So combining these two facts, we see that the Fourier feature mapping also makes the NTK into a stationary kernel. And this gives us a direct way to manipulate the width of that kernel. All we have to do is change the scale of the matrix B. And this is the big punchline here. So changing this single scalar value has a huge effect on how well the network can learn different frequency components of the training signal. If we change the standard deviation of our random B matrix, we can traverse this performance trade-off. So here I'm showing an image encoding that is encoded in a coordinate-based MLP and is supervised on every other pixel value. And in the middle, I have a trade-off curve of the PSNR versus the Fourier feature scale on the x-axis. Higher PSNR is better. And then finally, on the right, there's a central slice of the 2D kernel function. When the scale is too small, the network struggles to learn the high frequencies, and we get an over-smoothed output. When it's too high, the network overfits and then exhibits bad high-frequency aliasing. So we find that for this task and many others, a simple grid search can suffice to find the best scale value. And just to remind you again, all this variation is created from just changing this single scalar parameter. So one reasonable question to ask is, what random distribution should you sample B from? And surprisingly, it doesn't really seem to matter. So here's a plot showing the performance on the same 2D image regression task, but for 4 different distributions of B. You can see that each color traces the same performance curve when you plot the PSNR versus the standard deviation of B. So this helps reinforce the take-home message that all you really need to do in practice is pick the right scale for B, and you'll be close to the optimal performance. So in our case, we just choose Gaussian distributions for our experiments. Now, this technique is applicable for training coordinate-based MLPs as an alternative to like a low-dimensional arrays for representing a variety of low-dimensional signals. So in this first example, we train an MLP to regress the continuous 3D occupancy function of this dragon. Here, we train an MLP to represent the 3D volume density inside a human brain. And instead of supervising the ground truth 3D measurements, the network is actually indirectly supervised in the Fourier domain with MRI measurements. And then in this final example, we train an MLP to represent a neural radiance field, or NeurIPS, which is a view synthesis method that I'll explain a little bit more later. In all of these cases, what we find is that the Fourier features allow you to represent much higher frequency details than just a naive MLP. I think it's often nice to see the corresponding code to these sorts of problems because, at least in this case, it really shows the simplicity of the method. So before, we would just take our input coordinate and pass it into the network. So now we have our input coordinate, but then we also have this randomly sampled B matrix. And before we pass this into the network, what we're doing is we're just multiplying the input coordinate by this B matrix and then taking the sine and the cosine of it, and then just sort of stacking these all up and then passing it in. So this B matrix has 2 new parameters in it. Scale, so it's a normal distribution with scale and then the number of features. Scale is the thing I just described. In practice, you just do a grid search over a few different scales. And then the number of features is the number of projections you want to create. And in practice, we find that it doesn't really hurt to add more. So you should really just add as many as you can. Adding more obviously has a computation cost. So you just play that trade-off. But it does asymptotically sort of level off as you add more and more. So in summary, we found that a simple Fourier feature mapping enables the tuning of an MLP's NTK so that it is able to converge to high frequencies. One interesting avenue is to explore whether this finding could be applicable to other domains. I think there's a potential use case in robotics where you have a lot of these low dimensional inputs, such as like joint angles or velocities. And you might be interested in a more high dimensional output, not just a very smooth output. There's also a lot of work recently that are in like neural ODEs and these other types of problems that again have these very low dimensional inputs. And this sort of Fourier feature mapping could potentially allow you to capture these higher frequency outputs. Another interesting question is whether you can get the same benefits by using different network architectures. There's a recent paper out of Stanford called Siren, which uses sinusoidal activations instead of ReLU activations. And they're able to solve the same sort of low dimensional tasks that we look at here. So there's clearly a very strong connection between these two methods, but I think there's still some work to just figure out exactly what those connections are and how far they go. And I wanted to quickly highlight two papers that went up on arXiv this past week. Both of them observed that you could just take your typical, or you can replace your typical convolutional generator in a GAN with a coordinate-based MLP, since now we have a way to get these MLPs to represent high frequency details. And they show that you can meet, and in some cases exceed the quality of style GAN, which I personally was quite surprised at. You also get other additional benefits with these sorts of methods where you can sample them at arbitrary resolutions. And generally, I think this is a potentially interesting area to watch. So that's the Fourier feature paper. Next, I'll talk about this other paper, but before I do so, maybe I'll pause to see if there's any questions.
Hello.
Hi.
Can I maybe ask a question?
Yeah.
In the methods that you have, you just train it on one image, or do you have multiple images basically?
Right. So everything I'm describing here, you're training on a single example. So you're basically fitting a network to, it's not quite memorized because it does extrapolate, but you're fitting it to a single example.
Okay, and then you stop randomly, or so when do you decide to stop?
So for the image case, you can hold out some pixels that you use as a validation, and you could stop when that loss starts to decrease.
Okay, so you mean when it's close to the actual image for those pixel prediction that you hold as validation?
Yeah, so for the image case, I viewed a little bit more as a toy case because you know what you're trying to represent in the end. So it's not as practical. Where these methods really shine are for these more complicated methods like this NeurIPS case, which what this is you're taking a bunch of images and then you're trying to create this 3D representation, which you do not know what the ground truth is. So your supervision loss is reprojections of this. Mm-hmm. And in that case, you would hold out a few of those reprojections and use that as like a validation loss.
Okay, and here the input is just XY coordinates, right? Basically.
Yeah, so for 3D NeurIPS, it's a little bit more complicated. It's XYZ, and then it's also taking in the view direction, but it's the same general concept.
Okay. And do you know for the two papers that you showed, do they also, I'm guessing they are not doing it for just one image. They are just using it in the whole big network over a big set of images, right?
Yeah, so for these GAN papers, they train it like a normal GAN. The main difference here is where you would normally have a convolutional operator to generate the image. In this case, what they're predicting is these papers do it in slightly different ways, but the way you can think about it is they're predicting the weights of this underlying network so that you could pass in any coordinate and then produce an image from that. So it's sort of like a hyper network, if you're familiar with that term, where what you're predicting is the weights of this network.
Okay. Because to me, it seems to me a bit tricky, like how they associate different coordinates to different images. Because let's say if you want to learn a distribution out of many images, by default, a particular coordinate shouldn't tell you which image it is, right? You should have some sort of randomness. So probably they have some random sampling at some point that is added maybe to the coordinates, right?
So they don't actually add it to the coordinates. What they do is, if we look at this network architecture, they take a random sample, and then that random sample generates the weights for this entire network. So basically, each random sample generates like a new network, and then that new network, you could pass in all the XY coordinates to produce an image.
Okay. Okay. Yeah, I need to have a look to see what they are doing. Okay. But
it's definitely a very different way of thinking than like a traditional conv network.
Yeah.
But the beauty here is once you have these networks, you can pass in whatever coordinates you want. So you can sample the image at sort of infinitely high resolution if you wanted to. Now, it's probably not going to look very great, but there's no restriction on how finely you sample. Okay. And this is why it's sort of picked up, because this continuous representation, particularly for representing these 3D objects, is very compact compared to something like a volumetric grid. So for like the NeurIPS example I showed earlier, you could describe these big scenes in only a few megabytes of network weights. Whereas if you wanted to describe it volumetrically, it would take gigabytes.
Okay. And compared to the other method that you mentioned, they just changed the nonlinearity. What are the pros and cons of your method compared to their method, for example, in terms of quality or easiness to implement or the network capacity?
They're both pretty easy to implement. So in their case, in addition to changing the activations, they actually have to also change the initialization for each layer. So it kind of comes down to how easy that is in whatever package you're doing. But conceptually, it's fairly simple. I think the jury's still out as to like where one is better than the other. I found personally that like both of them tend to work well. In some cases, like I find that Sirens works better if you just only care about memorizing a target. So if you just want to memorize an image, whereas these Fourier features work a little bit better for generalization to make sure that you don't end up in like overfitting regimes. Mm-hmm. But in practice, I think they are very related, because if you think about it, so these Sirens, by replacing the first layer or the activation with a sinusoid, that's kind of what we're doing here. In our case, we're just fixing it, and then we're feeding a sinusoid. We're feeding it through a sine and a cosine. So if you make ours learnable, then you essentially have the same network. We find that when we make ours learnable, it doesn't really make a difference. So that's one point.
But in terms of the network size, if you are saying that you can represent much bigger volumes in a shorter amount of representation, is your network like effectively lighter compared to theirs?
Because no, so they also do the same thing where they're using these coordinate-based networks.
Okay.
So they get the same advantage.
Okay. Okay, thanks.
Thanks, Matt. There are also questions in the chat. I saw Mehdi is asking questions, maybe.
Okay.
And then I do have a small follow-up as well. People are raising their hands. That's great. I mean, if people can maybe keep questions a bit short, so we can all have their own, that will be great, because I think it's very interesting work. So we are all very curious.
Okay, so it looks like, can you modify B or infer it from your data? So if you're asking modify it in terms of like make it a learnable parameter, and the answer is yes. We find that it ends up just not really changing during the optimization procedure. And as a result, it doesn't improve the results by allowing it to modify. And then can you infer from your data? I think that's a really interesting question. We sort of explored this a little bit, and I think the answer is yes. You can take into account the the frequency statistics of the data you're trying to represent, and then choose B based on those frequency statistics. I don't have any like hard results for you at the moment, but I think the general answer is yes. Okay.
Maybe I can ask my question super quickly. Can you hear me? Yeah. So I've actually been working for a while with coordinate-based MLPs, and so when you guys first proposed the positional encoding in NeurIPS, I got very excited about it because we're also struggling with high frequency details. So we work in a conditional case, meaning that we have a large data set, and then we're learning this coordinate-based MLPs that are conditioned on latent encode. So basically, we've experimented with applying positional encoding to that setting. And back then, this new paper did not come out yet, and we saw that in practice, if you have a large scale data set in your conditioning, then this trick doesn't really work as well. Like we were not getting a big improvement, but I guess it makes sense with respect to the theory, because now you're kind of like hypothesizing the input of the MLP of being lower dimensional. So if you condition on latent code, then you have a much larger dimension. So I guess it makes sense. So I was just wanted to know. So it seems like the way to make this work with conditioning is to use to learn the weights of the network rather than conditioning these MLPs. And I just wanted to know your take on it. Why is it the case, or if you think it is the case?
Yeah. So the next project, I'll sort of touch some of those questions. In terms of the positional encoding with when you have these late encodes, did you apply the positional encoding to the late encode or just to the?
I try all. I try to apply it to the late encode. I try to apply it just to the XYZ.
Okay, I guess I'm kind of surprised that you didn't see much help, because I know in practice when I've taken like deep SDF and applied it, and it does seem to help, at least in some experiments that I've done.
Okay, so I did an analysis where I was making the data set grow more and more, and the more the data set was growing, the smaller the impact of positional encoding, to the point where with a very large one it was not. So I was just wondering. Okay, interesting.
Yeah, I think one other note is there's nothing fundamental that says that these networks can't represent high frequency details if they're trained long enough. The real question is like, how long do you have to train it to get that benefit? And it's possible that when you're training over multiple examples, that somehow changes the training dynamics to help to also help represent these higher frequency functions. Cool. That might be something that you're observing.
Yeah, thank you for feedback.
I have a quick question, if I may. Yeah, how does this compare to just taking the DFT of your data and then training an MLP on the DFT transform? Is there maybe some connection?
I think this is different. And then one question you have to ask is if you can always take the DFT of your data, if that always makes sense. So in the image case, maybe, but in some of these other cases, I don't know if you could do that. I'd have to think about it a little bit more, but I do think that they are slightly different.
Okay.
Yeah, sorry, I don't have a more concrete answer.
I know, don't worry, it's fine. I was just curious. Yeah, thanks.
Okay, I think maybe I'll move on. We can ask, if you have more questions, we can discuss them at the end. So I'm going to talk about this new project called Learned Initializations for Optimizing Coordinate-Based Neural Representations. And this is going to be the first time this project has been shown publicly. So yeah, that's fun. And it should show up on arXiv tomorrow. So this is a sneak peek. And what we're going to do is consider the exact same type of network. So these coordinate-based MLPs. And for now, we'll just stick to this 2D image regression case. Now, these networks are parameterized by a set of weights, which we're going to just call theta. And what we're curious about in this project is how important the initialization of those weights are. At the start of training, if we render an image with these initial weights, we'll obviously get a non-meaningful output. In this case, the output just looks gray. As we train the network, the weights, or theta, will change to fit to our target. And this is just a toy illustration of the weights moving through some sort of weight space. The optimization process can take a very long time depending on the type of problem. In this image regression case, it's not that bad. It only takes maybe 30 seconds to optimize. However, for more complicated representations like NeurIPS or other 3D representations, this optimization could potentially take hours or days. And this is important because we have to perform this optimization for every new object we want to encode. Unless we incorporate some other tricks, but just in the bare case, we have to redo this optimization every single time. So if I have to take 2 days or a day to train it for every single target, that's not really that great. So in this paper, we proposed using meta learning to help speed up this optimization procedure. And then we also find that meaningful priors emerge from using meta learning. So more specifically, we're interested in gradient-based meta learning approaches, and we consider 2 methods. So one is mammal and the other one is reptile. In both of these cases, what we want to do is find an update to the initial weight parameters, theta naught, so that the destination can be reached more quickly. This update is depicted by this orange arrow. And mammal accomplishes this by unrolling the optimization and then calculating the gradient all the way back to the initial parameters. This is computationally expensive since it requires calculating second derivatives for each inner iteration. And in practice, this means that we are only able to unroll a few steps. Reptile, the other method we use, is a simplified version that is a first order. And in practice, the algorithm is really quite simple. All you really do is you train the network so that you end up in some place like this red point, and then you just move your initial weights in the direction of that. So in practice, it's like a couple lines of code. So yeah, we now update our initial weights, and then we repeat the procedure. So we fit to a new target image, and we calculate how we should move the initial weights, and then we update our weights to those in that direction. At the end of this whole procedure, we're left with a new set of initial weights. If we just render an image with these initial weights, you start to see, in this case, there's like a little face hiding. So this is where the network, or this is where, if everything works out correctly, if we try to fit a new image, it can fit to that image significantly quicker. The other hope is that this new region of space that you're starting in is maybe a little bit more meaningful for the task at hand. We can talk about that a little bit more later. So we can take a look at some results. Here, we want to fit this target image and come up with the network weights so that we can reproduce this image. If we just use a standard initialization, as you can see, we're not getting anywhere very quickly. However, when we start from the initialization that was learned using the meta learning procedure, we very quickly are able to fit the target image. After 2 steps, you're basically matched it. And we can take a look at some numbers, and what we see is that on average, it takes 37 steps to reach the same accuracy as just 2 steps from a model that was initialized with the meta-learned weights. Now, interestingly, if we fit an image that isn't from the same data set that the meta-learning was optimized over, so the meta-learning was optimized over the SLEB data set, which is a data set of faces, what we see is that we're still able to fit a target quickly. So one natural question is, have we learned a way to just quickly assign pixel values, or is there a more like data-dependent prior involved? And we do some experiments to help tease this apart, where we train across different data sets, in this case, SLEB, ImageNet, a data set of text values, and then a data set of like 2D SDFs. And then we do the test time optimization on images from each of those data sets. And what we see is that there is a correlation between the data set it was trained on and the data set it was tested on. So it does seem that the meta learning is encoding some sort of data set specific prior. Another experiment we did was we fit the target image, the model or the network weights to different target images. And then we interpolated the network weights between those resulting optimized weights. And if you do this with the network that had the standard initialization, what we see is that the interpolation produces these really messy outputs. This isn't too shocking because the final weights end up at very different parts of weight space. Now, what's kind of cool is with the meta initialization, the interpolation between the weight space produces a much cleaner result that is very similar to just bilinear, like linear interpolation. So images are great, but not the most practical. So we'll move to maybe a little bit more interesting setting. And the goal now is to essentially apply the exact same meta learning setup, but to neural radiance fields or NeurIPS. And since I've mentioned it a few times, but haven't actually described them, I'll describe them a little bit more in depth now. So a NeurIPS is a representation of a 3D scene. And if we have some sort of camera position and orientation, we can render that scene by shooting a camera ray out into the scene and then taking samples along that ray. And then for each sample, we pass it into this same fully connected network, and we produce a color and a density sigma. You can think of the density as sort of how transparent that location of space is. So these values along the ray are then integrated using volumetric rendering to produce the color that that pixel represents. Now, the original NeurIPS model also passes in the view direction of the camera in addition to the XYZ coordinates. For our examples, we just skip that for simplicity. And the original NeurIPS network also uses two networks, one for like a coarse and one for fine to get higher details. For our experiments, we just use a single network out of simplicity. Now, for this project, the important part about NeurIPS is that the supervision relies on multi-view consistency. In the NeurIPS paper, most of the results that they have, it's always trained over 20 or more images. So now that we have some background, the question is, can we use this, this type of model in the exact same meta-learning framework? Now, in this case, we're going to train on ShapeNet chairs. During each meta-learning optimization step, we fit a new chair from a data set. And each chair has 25 views. And basically, it's just one chair, we fit it, we update the initial weights, then we fit another chair, update the initial weights, and then in the end, we get these new learned initial weights. We can then test time optimize for a new chair quicker when we use these initial weights. And this is what this plot is showing. So after 100 steps, you're doing significantly better than if you are training with completely random initial weights. Now, it's worth noting that during the test time optimization, we're still viewing 25 views of the chair. And this is the same number of views that we use during the meta learning procedure. So one question you could potentially ask is, what happens if we view fewer chairs? And if we go to the extreme, what happens if we view only a single chair? So this breaks the NeurIPS assumption because we are no longer providing the multi-view supervision that is necessary. So when we train the model, we see a nonsensical output. Now it's worth noting that if you render from the viewpoint of the input, this model would look correct. But in every other view, it's going to look incorrect because there's just nothing to supervise with multi-view consistency. So the punchline is, what happens if we now initialize the network weights using the weights that we learned in this experiment? And surprisingly, we're able to capture the 3D information about the chair. And it's worth re-emphasizing here that during the optimization procedure, the only thing we're changing is the weights that we're initializing the network with. The architecture, everything else is the same. And it kind of shocked us that we're able to capture these 3D priors. Now, recall that during the meta-learning procedure, each optimization had access to 25 views of the chair. One cool thing we found was that we could just provide a single view of a chair during each meta optimization step, and it could still capture a 3D chair prior. So in this case, MV meta stands for multi-view meta, and SV meta stands for single view meta. Now it's worth keeping in mind that for all of these methods, we only observe a single input image during the test time optimization. Here are some additional results on different classes. And I want to note that these are by no means state-of-the-art for a single image reconstruction. But I think the cool thing here is that this is just a byproduct of meta-learning. And it really goes to show how much you can get out of just changing the initialization. So without any of the many other tricks that people play for single view reconstruction, here we're just using a standard NeurIPS network with a different initialization during test time. So let's go back and consider the assumptions that the original NeurIPS model makes. It assumes that you have a lot of input data that kind of look like this, where there's multiple images of the same object, all under the same lighting and the same general appearance. So I just showed you that this meta learning could potentially help reduce the number of photos needed, at least in the case of where there's very strong priors like ShapeNet. Now, what happens if you have different lighting and different appearances? Well, a good example of data that has this is the phototourism data set. So here we have a lot of photos of the same landmark taken at different times of day under different weather conditions. Now, this just breaks the original NeurIPS assumption. If you try to train a normal NeurIPS on this, it tries to fit all these different lighting conditions at once, and you kind of end up with a blurry mess. There's been some recent work, NeurIPS-W or NeurIPS in the wild, that propose a way to modify the NeurIPS architecture to account for these changes of appearance. Their end results are really good, and I'd recommend checking out the videos on their website if you haven't seen them already. But the key point is that they had to make a number of architectural modifications and changes in the training procedure to get this to work. Now, what we're curious about is, could we just use this very simple meta-learning trick and help mitigate some of these issues that you get from appearance changes? Now, one of the advantages with the meta-learning setup is it is, one, very simple, and then two, it doesn't require any changes to the underlying model. We can just use the standard NeurIPS network. And so the way that this works is we have our network fit one image in the data set. Then we update our initialization so that it could fit that image quicker. Then we have it fit another image in the data set. We update the initialization, then fit another image in the data set. And we just keep doing this one image at a time. And surprisingly, we find that this is able to kind of capture the 3D information of the scene. Now, once we have these meta-learned weights, we can test time optimize on a new target image. So this image on the left. And what we see is that we can render an image that, as you can see, it's trying to replicate the target. It's still a little bit blurry, but you can see the target image there. Now, if I do this with just a normal network that has standard initialization, you would also get results like this. But the minute you move the camera, it would look bad again. This is the exact same as the chair case. However, in our case, since we are working from these meta-learned initialization, we can move the camera to match the pose of these top images. And we see that we get meaningful results that are now in the style of our target image that we've test time optimized for. And here's a grid that just shows a few different examples, where on the left, we're test time optimizing for the image in this left column. And then we're viewing that NeurIPS model from the poses in these top images. We can also do fun things where we interpolate between the different poses, while at the same time interpolating the weights of the network for these different test time optimization steps. Now, hopefully these videos aren't too choppy, given that this is Zoom, and if they are, they're all on the website, which you can view later. So here are two more examples. And so in conclusion, it's clear that these initializations can be very impactful. So if you have a data set that you're able to train over, this is a very easy setup and could potentially take you pretty far. Yeah, and that summarizes this particular project. Here are websites that are associated to each of the projects, and I wanted to quickly highlight again that this work is by no means my own, but really the work of many. And maybe we can switch back to Q&A. I'm happy to answer questions about this project or the original Fourier Future project.